Welcome to the Spaceship Controller in Unity tutorial mini-series, which will consist of 5 videos. This series is primarily for late beginner to early intermediate game devs. You understand basic coding principles, you've dabbled in a game engine or two, and you're ready to improve your skills. In this first video, we're going to plan out a spaceship controller in Unity that supports both keyboard and gamepad, as well as being able to switch between 2 different playstyles, which I'm going to call arcade and sim. There will be a break between videos during which I want you to try scripting it for yourself, based on the outline that we create here. Then in the second video, we'll actually write out that full script. I can then show you how I did it, and you can compare your execution with mine. In the third video, we'll make another outline for adding weapon functionality to our ship. We're going to go over 2 different types of ranged weapons, projectile and raycast. We'll also learn a bit about object pooling and particle systems. Once again, we'll have a little break between videos during which you can try scripting it out for yourself based on the outline that we make in that third video. Then in the fourth video, we will write out the full script again, compare notes. Then in the fifth and final video, I'm going to show you a cool way to handle switching camera views between the interior cockpit view and an external view of our ship using Cinemachine. Now before we write any code, we want to be very clear about the behavior we're trying to create. When our desired behavior is well defined, the script becomes much easier to write. So first, let's define that behavior. Our ship has a few major responsibilities. First, it needs to read player input in a way that works for both keyboard and gamepad. Second, it needs to support 2 distinct control schemes. Like I said, we have arcade mode and sim. Arcade mode is meant to feel accessible and forgiving. We're going to have the left and right input yaw the ship. Forward and backward input should control the ship's pitch. And in arcade mode, we're not going to use rolling at all. When the player lets go, the ship should also naturally just level itself back out, so the player doesn't have to worry about that. Throttle is also going to be simplified in arcade mode. Pushing forward speeds us up, pulling backward slows us down, letting go returns us to a nice just kind of cruise speed. In sim mode, the ship is going to feel quite a bit more involved. Left and right input is going to roll the ship instead of yawing it. Pitch is still going to handle, our up and downward direction, and then we're going to have yaw be applied with separate bumper inputs. The ship is not going to auto level. Throttle is also going to become persistent in sim mode, so if you release your joystick, we're not going to slow down or speed up. The player needs to deliberately adjust their throttle value over time, and then they can keep it there for more precise control. Then third, we want the controls to feel smooth and natural, not choppy or jerky. Fourth, we want maneuverability to change with our speed. What I mean by that is if we're traveling at a low speed, it should be really easy to turn our ship. But if we're going at a much faster, high speed, we want those turns to be a little more difficult. We want it to be a little less responsive if we're going super fast. And then finally, we want looping engine audio that reacts dynamically to the current engine power by adjusting its pitch and its volume. So if we're going really fast, the pitch is going to go up and get a little louder, You get the idea. So even though this is just one controller script, it's going to address several needs. Input, mode-specific maneuvering and thrust logic, smoothing, maneuverability scaling, which is what we were talking about, where we're nimble when we're moving slowly and a little more stiff when we're moving fast, and then reactive engine audio. This should give us a good vision to help keep our script organized into small, focused methods. Now that we have an overview of what we want, we can write our script, right? Maybe, but that's not what we're going to do here. Let's first refine our outline by writing it out in what's called pseudocode. Basically, we're just going to write things out in a way that looks kind of code-like, but we're not actually following the rules of coding. It's like writing an outline for your story. It's going to help us stay focused, stay organized, not get bloated or confused or off track. So here's some things that we're going to need to handle every frame. Reading and smoothing the player's input. If we're in arcade mode, we're going to handle updating the arcade style rotation and the arcade style speed. If we're not in arcade mode, then we're going to update our sim rotation and update our sim speed, because those are going to be calculated in different ways. And then we're going to move the ship forward every frame using whatever our current speed is that we've calculated. Then we're going to update our engine audio based on our power level. So at a very high level, meaning not getting into the details, that is pretty much the whole controller. So we're not having one gigantic method that handles all of this. We're making a sequence of small steps that each solve one clearly defined part of the problem. So let's walk through the main ideas one by one. First, we're going to talk about the input. We're going to use Unity's new input system, their new input system that's been around for like 10 years, and we're going to use that with input action reference fields so that we can drag actions in through the inspector. We're going to have a vector 2 for steering, a float for throttle. We're going to have 2 buttons that we referenced for our left yaw and our right yaw. This should give us a flexible way to support keyboard and gamepad without hard-coding device-specific logic all over the place. So to break these concepts down further, steering is our directional input for turning and pitching. The throttle is our engine, which can increase or decrease power based on input. And then our yaw buttons are going to be extras that we just use in sim mode for yaw control. Now let's talk about smoothing. Raw input tends to be abrupt, especially on keyboard where your values usually jump immediately from 0 to 1. It's either pressed or it's not pressed. So instead of using the raw input directly, we're going to smooth it over time. The pseudocode should look like this. We'll have something called smoothed steer, which is going to equal gradually move toward whatever the raw steer is. We're going to have smoothed throttle, same principle, gradually move towards whatever our raw throttle is. In the actual script, this is done using what's called interpolation, with a time-based factor. The idea is pretty straightforward. Instead of teleporting instantly to the new input value, we blend toward it over time. In mathematical terms, this is just a controlled interpolation. You can think of it like this. New value equals blend between current value and target value. That gives our motion and our input a softer, less twitchy feel. Next, let's talk about rotation. This is kind of the most important thing of all of this. When you're dealing with 3D space, especially with a flying machine of any kind, you have 3 main rotations. Pitch, which controls your up and down. You have yaw, which is your left and right. And you have roll, which is rolling over the z-axis, the forward axis. In Unity, these correspond to local axes. So you have pitch, which happens around the x-axis. You have yaw, which happens around the y-axis. And you have roll, which happens around the z-axis. So when we rotate the ship, we are applying rotation around one of those local axes. In pseudocode, we could say this. Rotate around local up axis for yaw, rotate around local right axis for pitch, and rotate around local forward axis for roll. It's important that we have our ship rotate relative to itself and its current orientation, not the world axes. So we need to use a local rotation. Now let's talk a little bit more about our 2 flight modes. A big part of our premise here is that we're going to have 2 modes that we can swap between. We're going to have arcade and sim. In arcade mode, horizontal steering becomes yaw, rotating around that y-axis. Vertical steering becomes pitch. We're not using roll in arcade mode at all. And we're going to have the ship auto level whenever our input is released. So in pseudocode, we could say yaw from steer x, pitch from steer y, apply yaw and pitch rotation, gradually bring pitch back to 0. Gradually bring roll back to 0. Those gradually moving back to zeros are so that we can have the ship settle back toward kind of a neutral, straight and level orientation. Again, this is a kind of control mode that is meant for beginners, people who are not super comfortable with flying. It's going to be more forgiving for them because if they do nothing, their ship's going to level out and fly straight. In sim mode, naturally our rotation is going to be a little more complicated. Our horizontal steer becomes roll. The vertical steer remains pitch, and now yaw is going to come from separate buttons. There's no auto leveling happening here. So pseudocode for that could look like roll from steer X, pitch from steer Y, yaw from left-right bumper buttons. Then we apply the roll, the pitch, and the yaw. This is all to make sim mode feel more fine-tuned, as it gives the player much more precise control over their ship and how it moves. Now let's talk about inverting pitch. Pitch direction is one of those things where you simply have to have options, or you're going to have very irritated players. In order to handle the crazies out there who think that pushing forward on a joystick should move their ship upwards, you lunatics, we can create a small helper method that processes the pitch input. In pseudocode, we can say, take the vertical input, flip it to match our default control style. Then if invert pitch is enabled, flip it the other way. Then return our final pitch input. This makes it so all player logic passes through this one centralized place. Generally speaking, if we can centralize logic, we want to. Okay, now we're going to talk about speed and throttle. Arcade speed, once again, is pretty straightforward. If the player pushes their throttle forward, we target our max speed. If they pull back, we target our minimum speed. And if they're pressing nothing, we just target a nice cruise speed. Then instead of snapping instantly to that target, we move toward it over time. So in pseudocode, it looks something like this. Target speed equals cruise speed. If throttle is forward, target speed equals max speed. Else if throttle is backwards, target speed is min speed. Then we move current speed toward target speed. This helps the flying in arcade mode feel more like controlling a character on the ground. Push forward to walk forward. In sim mode, naturally, it's going to be a little more complex. Instead of directly choosing a target speed each frame, the player adjusts a persistent throttle value. That throttle value is then normalized between 0 and 1. Then, our speed is calculated by mapping that normalized throttle into the range from minimum speed to maximum speed. Stay with me here. In pseudocode, we can say, if throttle input exists, increase or decrease our normalized throttle. We're going to clamp our throttle between 0 and 1, and then we can say that current speed equals value between min speed and max speed based on our normalized throttle. So instead of storing raw speed as our main player-controlled value here, we store a normalized control value and we convert it into speed afterwards. Why are we doing that? Well, it makes the system easier to reason about and easier to expose in UI. We're not addressing UI in this particular series, but if people request it, I would be happy to make an example of syncing up all this logic with a UI visual element. But the gist of it is, imagine any sort of flying game where you have throttle power and you've got maybe one of those bars, that maxes out up here and with no power it's down here, right? If that's represented by 0 to 1, we're always going to know it's either 0% full, 100% full, or somewhere in between. And that makes dealing with something like a bar like that much easier, much clearer. Let's talk a little bit about the math of normalization. A lot of what we've just talked about relies on normalization. A normalized value is just a value expressed in a standard range, usually something like 0 to 1. It can help to think of it as a percentage, like 0 to 100%. If I say I have 700 out of 1,000 of something, you could just as easily say that we have 70% of something. In a normalized value in terms of 0 to 1, that would just be 0.7. So in this example where we have a minimum value, a maximum value, that could be a 0 minimum value, a 1 for a maximum value, and the mid value could be 0.5. When we go into code and we use something like mathf.inverse lerp, that's what that's doing for us. Given a value between minimum and maximum, then tell me how far along that range it is from 0 to 1. And then mathf.lerp is going to do the reverse. Given a normalized value from 0 to 1, return the actual value between minimum and maximum. So in this script, we're using normalization for our normalized speed, our sim throttle, the engine audio response, and our maneuverability by speed. And speaking of maneuverability by speed, we want the ship to turn easily at lower speed, less easily at higher speed. So we normalize the current speed, 0 to 1, then we use that normalized speed to evaluate an animation curve. I will explain that momentarily. We're going to use the result as a maneuverability multiplier. So in pseudocode, it might look like this. Normalized speed equals how fast are we between the minimum and the maximum. Maneuverability equals evaluate the curve at normalized speed. And then we can say adjusted turn speed equals base turn speed times maneuverability. Now, I really like using animation curves pretty much whenever I can. It makes for a nice visual way to tweak values in the editor. And it comes pre-built with several really nice options that can often get you most of, if not all the way there, in terms of feel. From a math perspective, this is just a function. We're saying maneuverability equals F speed, where F is the curve that we design. So once our ship's been rotated and its current speed has been determined, movement becomes pretty straightforward. In pseudocode, we can say position plus equals forward direction times speed times delta time. If you aren't familiar with what any of that means or how it works, you should. Transform.forward is a direction vector that points out the front of the ship. Multiplying a direction by a speed gives us motion per second in that direction. So that's going to give us movement. Then, multiplying by delta time makes the movement frame rate independent, which is very important. Without delta time, the ship would move farther on faster running machines and less far on slower running machines. Now let's finally jump into everybody's favorite subject, audio. Our plan for the engine audio is built on the same normalization ideas that we've been discussing. We want pitch and volume, pitch in this case being not, this kind of pitch. We want the pitch and the volume to respond to our engine power. This is actually more straightforward in sim mode because we can measure our power with the normalized throttle. In arcade mode, we can get a pretty reasonable approximation by using our normalized speed. So in pseudocode, we can say, if the sim mode is active, use throttle value as engine power. Otherwise, use the speed value as our engine power. Then we can say that our target pitch equals lerp between our minimum pitch and our maximum pitch, and our target volume equals lerp between minimum volume and maximum volume. Basically, as we're getting faster, we get higher pitched and louder, and as we get slower, we get lower pitched and quieter. Then we're going to smoothly move our current audio values towards our target values. Exact same concept we talked about previously. Normalize a value, then use lerp to convert that into the final output range. This can all kind of seem like gibberish when you're first starting out, but I find it helpful to keep my eyes out for patterns, and when trying to create something, see if I can do it with the techniques I already know. Then when you inevitably hit a wall, try coming up with new solutions. This helps you to practice the things you do know, while being more intentional about learning new concepts when the need arises. So let's go over a clean pseudocode outline of the entire script. We're going to call this ship controller. We're going to have these variables: current mode, invert pitch option, input action references, speed settings, rotation settings, smoothing settings, maneuverability curve, our engine audio settings. In our start, we're going to say clamp the starting speed, and if we're in sim mode, convert the starting speed into a normalized throttle, and set up our engine audio. Then in update, we're going to read and smooth our input. If we're in arcade mode, we're going to update arcade rotation and update arcade speed. If we're in sim mode, we'll do the sim versions of those things. Then with the values we calculate, we'll move our ship forward, and we'll update our engine audio to match our ship's power. Then we're going to read inputs for steer vector, throttle float, and smooth both of those over time. For updating arcade rotation, we're going to get maneuverability multiplier from current speed, and we're going to get the yaw from our horizontal steer, and pitch from our vertical steer. Then we're going to rotate the ship. We're going to auto level the pitch and roll towards 0. For update arcade speed, we're going to choose our target speed based on the throttle's current direction. We're going to move our current speed smoothly toward our target speed. Then for updating sim rotation, we're going to get the maneuverability multiplier from current speed. We're going to roll from horizontal steer and pitch from vertical steer. And we're going to use yaw with buttons. Then we rotate our ship. For updating sim speed, we're going to adjust the normalized throttle over time. We're going to clamp the throttle, and then we're going to convert the throttle into actual speed. To actually deal with pitch, we're going to have a method called getProcessedPitchInput. We're going to apply the default pitch convention, and we're going to optionally invert it if the player doesn't like normal controls. We're going to have a method called getManeuverabilityMultiplier. We're going to normalize our current speed, and we're going to evaluate our curve to get a turn multiplier. Then we're going to have a moveShip method, which is just move forward by speed times delta time. Then we'll have update engine audio, where we'll determine our normalized engine power, we'll map it to a target pitch and volume, and we'll smoothly blend our audio values towards the target values. So I chose this particular tutorial to be this level of educational because this script in particular covers a ton of really foundational concepts all in one place. Reading input from the new input system, separating behavior into these bite-sized methods, using enums to switch between playstyles, working with pitch, yaw, and roll, specifically using local space rotation, smoothing with interpolation, frame rate independent movement with delta time, normalization with inverse lerp, value mapping with lerp, using curves as tweakable gameplay functions, keeping related logic centralized in helper methods. So with all this, you should have everything you need to start crafting your own script. Take a crack at it. If there are things you wish were in this plan that are not, add them. That said, I do recommend keeping the script very focused. You might be tempted to add weapon firing into this same controller, and you could certainly do that. But the more features you cram into a single script, the more unreadable and unwieldy it tends to become. So keep that in mind. But do your best. A week from today, I'll be releasing the next video, at which point you can compare your solutions with mine. If you can't get things working the way you expect, don't get down on yourself about it. It can be super valuable to try and fail, and then see later exactly where you went wrong. If you watched this video and you felt it was a bit too advanced, I highly recommend you check out the Math of Video Games series, as that one is truly for beginners. Thanks for watching, and I'll see you all on the next one.